Hi, this is our first video on hash tables. This gives kind of an overview of the hash table data structure and approach, and we'll get into more details in later videos. So remember the map abstract data type. We've gone into how to implement the map abstract data type using binary search trees in previous videos. The abstract data type of a map has the following important operation: contains key, so given a key, determine true or false whether the key is in the map. Find, given the key, so given a key, find the pair that contains that key or throw an exception if there is no such pair. Insert is given a pair and puts that pair into the map if it's not already present. And erase is given a key and it removes the pair associated with that key if there is any such pair. So we've already seen one solution to implement the map abstract data type. It's the self-balancing binary search tree, such as an AVL tree. And every one of those four operations is big O of log n worst case time when you use a self-balancing binary search tree, and that's fast. Also, the self-balancing binary search tree, since it obeys the binary search tree order invariant, keeps all of the keys in sorted order, and sometimes that's a convenient property. However, the self-balancing binary search tree is node-based, and that means it has poor locality of reference. We saw this come up between vectors and linked lists, that both a vector and a linked list stores a kind of a sequence, but the vector has better locality of reference because it stores all the elements in one contiguous array, whereas a linked list is a chain of nodes. Most likely those nodes are at very different memory addresses, so the nodes have poor locality of reference, which means the data structure can be slower because of cache misses. So that's also an issue with binary search trees. Trees are also node-based. Most likely the nodes of the tree are at very different addresses, and so we have poor locality of reference in the binary search tree as well. Now what we're going to cover is an alternative to a self-balancing binary search tree, which is a hash table, and it addresses some of those issues. It's a little bit faster than trees. It's constant time versus log n time with some trade-offs that we'll talk about, and it's more vector-based than node-based. However, a hash table does not store the keys in sorted order, so that's another kind of negative for the hash table. So let's get kind of the first idea down. This won't end up working out, and we'll have to amend this, which will add some complexity, but let's just get kind of the basic idea of a hash table down first. So our first idea is we'll just use a key directly as a vector index. So we'll create a big vector called v for vector, where we have this invariant that defines what an element of vector v is. So v, and we use a key as an index. So given a map key, we just look up the element at that index, and what v of key is a pointer to the pair that has that key, or if that key is not present at the moment, v of key is a null pointer. So for example, if we had a map that stores the pair of key 1 value cat, then the key is 1, so at index 1 we have a pointer to the pair 1 comma cat, and the pair key 4 value dog would be at index number 4. And indices 0, 2, and 3 are null pointers. I'm not bothering to draw them. That means that keys 0, 2, and 3 are not in the map right now. So here's what the pseudocode for that would look like. In order to determine if a key is present, we just look up v at index key, and if that's not null, then key is present. In order to find a key, what we do is the same thing. If v of key is null, then throw an exception. Key is not present. Otherwise, v of key is a pointer to the pair, and we dereference it. In order to insert a pair, we can say if contains key, return false and do nothing. Otherwise, v at pairs first. Pairs first is the key of the pair, so we just use the key of the pair as an index and set it equal to the address of that pair and return true. And erase is check that if the key is not present, we don't do anything, but if the key is present, we overwrite the v key pointer with a null pointer. So this is very simple, just 1 or 2 or 3 lines of code each, and we have constant worst case time for all these operations. So far, this looks pretty good, but there are 2 huge problems with this approach. It's not really practical. One problem is the vector might need to be humongous, and so huge to be totally impractical. So remember that the maximum value of a w-bit unsigned integer is 2 to the w power minus 1. So for example, an 8-bit byte can hold a value as big as 2 to the 8th power, which is 256 minus 1. 255 is the maximum value of an 8-bit integer. Or a 16-bit integer can hold a value as big as 2 to the 16th power minus 1, which is about 65,000. That can get really huge. Most likely we have 32-bit integers or 64-bit integers, and if we're using those as keys and any possible integer is a legal key, then this vector v is going to have to be astronomically large. So for a 32-bit integer, 2 to the 32 minus 1 is approximately 4 billion. So vector v would need 4 billion elements. And if this is a 32-bit computer where every pointer is 32 bits, that's 16 gigabytes of memory to make one hash table data structure. So that's 400% of the memory in an entry-level laptop. So this is not acceptable. If you buy a laptop and want to create a hash table data structure in it, but too bad, you need 4 laptops just to make one hash table to store some data, that won't work. That's not practical at all. And then this gets even more off the hook if we have 64-bit integers. 2 to the 64th power minus 1 is about 1.5 times 10 to the 11th gigabytes of space to store one hash table data structure. That's about the memory of 37 billion laptops. So is this going to work out that every time we create one hash table data structure, we have to buy 37 billion computers to store it on? I don't think so. That's not going to work. So that's one deal breaker right there. There's another big problem with this approach, which is that it was based on using the key of the map as an array index, but not all key types are unsigned integers. We want to be able to use other types. You remember with the binary search tree, all we needed of the key was that it was comparable, and so we were using strings, we could use floating point numbers, all sorts of data types. So we want to be able to use an int as a key that could be positive or negative. Negative numbers are never legal array indices. We'd like to be able to use a string. A string is not a legal array index, or a float, that's not a legal array index. Even user-defined types, like if I make my own class that could maybe be a key, I would like that to be something that could work. So that approach doesn't work either. So we can solve both of these problems by adding another component to this data structure called a hash function. So in general, in computer science, a hash function is a function, like a code function or a math function, that maps an object to an integer in a known range. And it's kind of a weird word. I think it's based on the idea of like a breakfast hash. This is a corned beef hash up here, or an egg hash. And the idea of this hash meal is that you take some ingredients, chop them up and make a big kind of mess. It's just a big disorganized mess. And that's kind of the idea of how hash functions work, is they take an object and kind of scramble up what it is into kind of a random-like integer, kind of a weird, unpredictable integer value. So here's how we use hash functions in our hash table data structure. We'll define a reasonable vector size m. So instead of these, multiple billion element vectors, we'll have a reasonable size of the vector, maybe something like approximately n, the number of elements in the vector. So if I want to have 16 elements in my map, maybe a vector of size 16, so m would be 16, a much more reasonable figure. And we'll create a hash function, and what the hash function does is it's given a key as an argument of any key data type, and that hash function will need to return a valid index in an m element vector. So hash key returns an int in the range 0 through m minus 1. We'll get into how to create such a function in the next video. It is a little bit technical and complicated, so hold that thought for now. So here's how we need to change how the vector is used. And now the invariant on vector v is that instead of saying v at index key is a pointer to the pair with that key, instead we'll say v at hash of key is a pointer to a pair with that key. So every time we want to look up the location of a pair, we grab the key of that pair, feed it into this hash function, call the hash function, it does some arithmetic and returns an index, and then that's the index that we use in our vector v. So here's kind of how that would look as kind of a sketch. The idea, again, is that we have this hash function, we'll define that next. It's given a key, which could be any data type, and it returns a index into the vector. So vector at index hash of key is a pointer to the pair that has that key, or null pointer if there isn't any such thing. So these hash functions usually do kind of unpredictable, wacky things. Like here's an example of what that might look like. This is just an example, but uh, my hash of key is key times 4 mod 5. So take the key, multiply it by 4, and then do modulus 5, so remainder of division by 5. So that means that if I take key number 4 and plug it into the hash function, 4 times 4 is 16, 16 mod 5 is 1, so the index in the table where 4 would go is index number 1. So 4 is not going at index 4 anymore, it's going at this other index 1. And similarly, key 1 associated with cat down there, if we plug 1 in as the key, 1 times 4 makes 4, 4 mod 5 is 4 again, and so index 4 is where key number 1 would go. So that's kind of the idea. We have this hash function, and it kind of scrambles up the keys so that instead of using the key as an index directly, it's scrambled up. It goes to a different index location than what the key is itself. So that's that hashing idea again. So there's still some remaining problems. One is how do we actually set up one of these functions? We'll get into that soon. There's another issue, a pretty big issue, called a collision. A collision is when two different keys have the same hash. And that's possible. So what if we wanted to insert key 1 and key 4, but hash of 1 and hash of 4 gave us the same index? That didn't happen on my example on the previous slide, but mathematically it could happen. It's a pretty serious problem, and we'll go over how to solve that in a later video.